Hello everyone, welcome to the 3.2 notes. This is called implicit differentiation. And so that is the technique we're going to use to find the derivative. But before we get there, we're going to look at this kind of warm up. And this says, which of the following examples could you find dy dx? Which ones look more challenging? So anytime we've been asked to find the derivative, we have had y solved for. So on first glance, the only one that I know is going to be super easy to find the derivative is example 1. And we know that the derivative of y with respect to x is just 9. So looking back through some of these, well, example 2, y isn't solved for. Example 3, y is not solved for, but actually it'd be pretty easy to do this one. So I'm going to give this one a check mark because all you have to do is add 3x squared to both sides and you get y equals 3x squared plus 4. And then the derivative of y with respect to x is 6x. So those two are honestly not that bad. And maybe you've never noticed that all of the problems we've had y solved for. But example 2 and example 4 would be pretty hard. So like example 4, if I would want to get y squared by itself, I'd have to subtract x squared on both sides, and I get 25 minus x squared, and then I would need to square root both sides. But if you do square root both sides, on the left side over here, you have to include plus or minus, and that just makes things really complicated. And so, yes, I solved for y, and I could find the derivative of that, but because of that plus or minus, that's just more complicated. And then for this one, okay, if I wanted to get, so like my kind of strategy is to get the y's on both sides, so I'd subtract this 3y on both sides, but I just can't get those two y's together. I can't like get one y because I cannot separate cosine and y. So this one right here, it's actually as it is, and what we know, like it's just not possible for us to find the derivative right now. And so implicit differentiation is used when we are not able to solve for the dependent variable, in which is like x is normally the independent variable, y is normally the dependent variable. And so this is a strategy we use when we cannot take the derivative easily because we can't solve for y. And there's a lot of functions, for example, example 4 right here, that I would never be able to solve for y for, but I still could find the derivative. And so before we talk about this, we just want to think about this phrase dy dx again. So remember, this just means the derivative of y with respect to x. And so a lot of times if I tell you to find like the derivative of y prime, oh, okay, let's say that y equals, oh, it came back. Let's say that y equals 9x plus 3. dy dx then is 9. But another way that you could write it is you could do d of dx, and then instead of like putting in a y here, you just put in parentheses what your y function is, and that's saying the same thing. It's this notation right here is saying like find the derivative of 9x plus 3, and that's 9. So that's just different notation. And so to understand this idea, we need to really think about what does this notation dy dx mean. And so here I'm going to find the derivative of y, and so normally like this would be dy dx, and you know that y equals x. So basically what this notation right here is saying is find the derivative of x. So it says the derivative of x, and then the denominator says with respect to x. So what I want you to notice about this, so that's how you would say this right here. It's the derivative of x with respect to x. What I want you to notice is that these two things match up. You're taking the derivative of x with respect to x, so the variables match up. Over here, this is asking us to find the derivative of x cubed with respect to x. So again, these are not the exact same things, but you're taking the derivative of something with an x with respect to x. And so in all the problems we've done so far, x has been our independent variable. But let's say that we're going to take the derivative of y to the 4th power with respect to y. That's what this means. It's the derivative of y to the 4th power with respect to y. And so we did change what our denominator looked like, but the important part is that these are both y's. And then finally, this last one, what this notation means is it's the derivative of t to the 6th power plus 5t plus 3 with respect to t. And so again, those variables match up. We have t's over, we have t's over here, and then we have a t over here, and those match up. Now, what's implicit differentiation is going to ask us to do, because y is not solved for, we're going to be asked to find the derivative of something that doesn't match up. So if you notice right here, what this notation is saying is it's saying find the derivative of y to the 5th power with respect to x. And this is a different kind of problem it's asking us, because it's asking us to find the derivative of a y with respect to x. And so y is still our dependent variable and x is still our independent variable. And so far we have not been asked to do a problem like that. And so this is the concept of like how you would do a problem like this, and then I'll kind of walk you through some procedures. But the concept's really important to understand this. So this example 1 says find the derivative of y to the 5th power if y is a function of f. So this part right here is our key idea. Y is a function of x. And what that means is that we can make y using x. X is our independent variable, so if we put x into our function, it will spit out y. And so what this means right here is f of x equals y. That is what it means for y to be a function of x. If I put x into the function, I'll get out a y. And so instead of thinking about this as the derivative of y to the 5th power, because we just talked about how y can be made using x, I'm going to replace y to the 5th power with an f of x, and then I'm going to raise this to the 5th power. So that is the same thing. I'm just thinking about y in terms of f of x instead of in y. And the reason I'm doing that is because now if you notice, we have an x and an x matching up. So we have the derivative of f of x to the 5th power in x, and that's like what we were seeing on that page before. Now, you might be at a place where you're recognizing this, but you might not, and that's okay. But that is a composite function. F of x is the inside function, and then that 5 is the outside function. So f of x is the inside function, and essentially x to the 5th power is the outside function. And so if I want to find the derivative of this, I just need to do the chain rule. So to find the derivative of x to the 5th power, I'd had 5, and then I keep the inside function in. This goes to the 4th power, so that's the derivative of the outside with the inside plugged in. And then I just have to multiply by that by the derivative of the inside. And so this is what the derivative of y to the 5th power is, if we think about y in terms of x. But we're not going to change it every time. We're going to keep it in the notation it is, because this would kind of be a doozy if every single time I had to do a problem, I had to change it into function notation. And so this is how we would think about it if we didn't want to change it into function notation. So same idea, we basically think of y to the 5th power as the outside function. So we would do 5y to the 4th power, but then we think about y, this part y, as the inside function, and we take the derivative of that inside function. And the derivative of y with respect to x, you would write dy dx. And that's equivalent to this, because this is just like, right, this is a derivative, and then this is just another notation for derivative. And so you were thinking about y as if it is an inside function. So like if you go back to this notation over here, this 5 right here is like the outside function. You take the derivative of the outside function. You think about y as if it were an inside function, so then you multiply this by dy dx. And so the other notation that you sometimes might see this in instead is, there's just like other ways to think about like the notation of derivative. So the other way would, if you thought about it as 5y to the 4th power, and then instead of using dy dx to represent the derivative, you can also use a y prime. And in these problems, they get kind of icky as we do them. Like they can get really long, and so sometimes people like using y prime instead of dy dx. But that is what the derivative of y to the 5th power would be. So that is the concept. You're viewing it as an inside function because y is a dependent variable. It depends on x. So you think about that y as if it's an inside function that depends on x, and then you take the derivative of the outside. So we're going to do one more example like this, and then I'm going to walk you through some procedures. So this is kind of the same idea. It says find the derivative of 2t cubed if t is a function of x. So we're finding the derivative with respect to x, because x is our independent variable. And so anytime you take a derivative, you take the derivative with respect to x. So we could create this t function because t is a function of because t is a function of x, t essentially equals f of x, because you create t by plugging x into your function. And so again, I could just think about this as taking the derivative of 2 f of x cubed. And then f of x is the inside function, so I basically would have 6 f of x squared times the derivative of the inside. And I just did, the reason that's a 6 is because I just did 3 times 2, and then I took I left the original function and I took the derivative of the outside. Or in other ways, if you don't really, if you're like, you feel like you got it, essentially what this is it's going to be 6t squared, because that's just the derivative of this outside part, and then we'll times that by the derivative of the inside, which is dt dx, because this part right here, what this represents, it's just the derivative of t. And then if you don't want to write dt dx and you would like to write it shorter, you would write the derivative of 2t cubed equals 6t squared times t prime. So the concept of implicit differentiation just can be confusing. And so one thing that might be helpful if you guys are still stuck and this is not making sense is read articles on the internet about it, or just watch a lot of different people talk about implicit differentiation, because a lot of times just people can phrase it differently and can connect more. And so if you want to watch Nancy Pye or Khan, or watch some, I've read a lot of articles on Quora.com to help me learn more about what implicit differentiation is. And so if you're feeling stuck, that is totally a place I recommend you go next. But at this point, we're just going to go through the process of how do you actually solve a problem with implicit differentiation. This is kind of the concept. I didn't want to just give you steps if we didn't explain a little bit why we're doing what we're doing. So here's the process. Basically what you're going to do is you're going to differentiate both sides of your equation with respect to x. And if you differentiate a term that has a y value, you will multiply it by dy dx. Or you can use, and that just stands for the derivative of y with respect to x, or you can use y prime as your notation. Then you will collect the terms with either, if you use dy dx, you'll collect those on one side of the equation, or if you use y prime, you collect that on one side of the equation. Then you will factor out your dy dx or your y prime, and then you will solve for your dy dx or your y prime. So these are the steps you need to use to go through these problems. And so feel free to just keep that handy as you do your homework, as you do these notes, refer back to them. So let's talk about what we actually mean by this. So this says differentiate x squared plus y squared equals 9. And so the reason we're using implicit differentiation is because y is not easy to solve for. So it's not easy to get the dependent variable on one side and just find the derivative. And so instead, I am going to use implicit differentiation. And so I am going to take the derivative of both sides with respect to x. And so I'm going to split this side. So I'll differentiate each term. So I'll differentiate x squared with respect to x, and then I'll differentiate y squared with respect to x. And then over here, I can just go ahead and do this over here on this side because it's just a constant. So the derivative of 9 with respect to x is just 0. So that's just going to go away. And then over here, the derivative of x squared with respect to x is 2x, because what we are taking the derivative with respect to, those two match. So that's super simple. But over here, we're taking the derivative of y squared with respect to x. And so those don't match up. And so because those don't match up, I'll think about this as the chain rule. So this will be the derivative of y squared is just 2y. I just think about it as 2y. And then I multiply that because the x and the y don't match up, because these don't match up. I multiply that by dy dx, because that is the derivative of that inside function y. So that was my step 1, essentially. My step 1 was to take the derivative on both sides. My step 2 is to collect all of the terms with a dy dx on one side. So I'm going to highlight this. This is kind of like an algebra when you would solve for x. So I'm just trying to get dy dx on a side by itself. So right now on this side, I have two terms. I have 2x and I have 2y times dy dx. And so 2x does not have a dy dx. So I'm going to move that over to the other side. And I'm just going to keep highlighting my dy dx just so we know where it is and we know that that is our goal. So I've done my step, and I guess this is step 2. Step 2 was to collect the terms with dy dx on one side of the equation. So I did that. And now I'm going to, it says factor out, but essentially I'm just going to try to get dy dx on its own. I don't have to factor in this situation, but sometimes you will. So to get 2y and dy dx disconnected, they're connected by multiplication. So I need to divide both sides by 2y. These two y's will cancel out, and I'll get dy dx equals negative 2x over 2y, and then that simplifies to negative x over y, because 2 divided by 2 is 1. And this is our answer. So that is the derivative of y, but we just had to use a different technique because y wasn't solved for. So the derivative of y with respect to x, the derivative of this problem is negative x over y. And so a lot of weird process, kind of a simple answer. So we're going to do a couple more. Same idea. This is a very similar problem to this last one. So if you want to try it by yourself, I recommend you do that. But I'm just going to go ahead and get into it. So I'm going to take the derivative of both sides with respect to x, because you always do it with respect to x because that's the independent variable. This ends up being, so the derivative of x squared is just 2x because those variables match up, but this one they don't. And so this will be negative 2y. So I kind of take the derivative this like normal, but then I always multiply it by dy dx. The derivative of x with respect to 0 is 0. And then I'm just trying to get dy dx on a side by itself. So I'm going to move everything that's not dy dx over. So this will give me negative 2y times dy dx over negative 2x. I'll divide negative 2y on both sides. And this gives me dy dx equals negative 2x over negative 2y. The negative 2's cancel out. So my derivative of y with respect to x is x over y. So there is your answer for that one. Okay, on to another. So a lot of times your answers are going to be like kind of like it looks that simple, a lot of times your answer will be something like x over y. But this next one is a doozy. So we did some like pretty easy ones to start off with. Now we're going to do a lot harder one. So just be prepared. Sometimes these problems get really, really nasty. So this is an example of a very nasty problem. So we're going to start off taking the derivative on both sides with respect to x. So it'll start off feeling fine. Okay, over here on the left side, the derivative of x squared is 2x. So this is just the same as last one. The derivative of y cubed with respect to x is 3y squared. And then because it's a y, not an x, I'll multiply it by dy dx. And then over here on the left side is where it's a little interesting because I have to take the derivative of that. But you might notice this. This is a product because it is 18x times y. So because it's a product, I have to use the product rule and implicit differentiation at one time. And so that's going to be icky. But the product rule is, I'm just going to start using it. It's the derivative of the first term. So the derivative of 18x with respect to x is 18. So that part's good. Times the original second function. So I'm only multiplying something by dy dx when I take the derivative of it. So because I didn't take the derivative of y, I'm not going to multiply it by dy dx. Then I'll do plus the original first function times the derivative of the second function. The derivative of y is 1, but then I need to multiply that by dy dx. So that is the start of this problem, and it really doesn't look too bad. So that was the differentiation step. My next step is I need to get the terms that both have dy dx's on both sides. But let me just take a second and just kind of clean this up real quick before I do that. So that side was fine, but I'm going to actually write it as 18y, and then I'm going to write it as plus 18x times dy dx. So that might not make that big of a difference to you. But basically, what I need to do next is I need to get these dy dx's on the same side, and then I need to get the things that aren't dy dx on different sides. So essentially, I'm going to subtract. So this part right here is one whole big term. So I'm going to subtract 3y squared times dy dx on both sides so that I can get that term over here. So these will cancel out. I'll have 2x equals 18y plus 18x times dy dx minus 3y squared times dy dx. So I've made some progress because now my dy dx's are on the same side. And then this is one big term. So you can't disconnect them yet until you use division. And then I'm going to move 18y over so that the dy dx's can be on a side by themselves. And so now I'm going to have 2x minus 18y equaling 18x dy dx minus 3y squared dy dx. So now the terms that have dy dx's are isolated on the right side. There's nothing else with them. And so this comes into my step 3, which we haven't had to do yet, and that's factor out a dy dx. So I'm going to write this over here on the left the same, but because both of these have a dy dx, I can just like factor them out as if they both had like a variable they shared. So I'm going to factor out dy dx. That's going to leave this term right here with just an 18x. So like this will basically leave because we pulled it out, and I'll have 18x. And then this one will leave too because I'll pull that out and I'll have minus 3y squared. So now I have factored out my dy dx. And then if I want to get them alone, well, now dy dx is connected to this expression by multiplication. So I will divide this whole expression over on both sides. These cancel out, and my answer will be 2x minus 18y over 18x minus 3y squared, and that equals dy over dx. And that is your answer. So, long problem, but really not that bad. I hope you believe that. It's okay if you don't. Okay, the next one is not as bad, and then we'll kind of try to move quicker through some of these other ones. So the next one's a lot shorter. So step 3, it says find the derivative of x equals sine y. So there is like kind of a tricky part to this, but we'll get there when we get there. So we're going to take the derivative of both sides with respect to x. Okay, actually I don't think it's that bad. So the derivative of x with respect to x is 1, and then the derivative of sine of y with respect to x is cosine of y, because that's the derivative of y, and then times the derivative of that inside, which is dy dx. And let's use the y prime because we haven't used that yet. So we're going to times it by the derivative of the inside, which is y prime. So remember, anytime we take the derivative with a y, we multiply it by dy dx or y prime. I'm just going to use a different notation this time, but if you wanted to keep using dy dx, that's fine. So I don't know why I said this one was bad. It's not that bad because we now just need to get y prime on a side by itself. So all I have to do is multiply cosine of y on both sides. And I'll get 1 equals cosine y, which equals y prime. Okay, that one wasn't that bad. Let's go on to our next one. I'll use y prime again for this one, and then I'll go back to dy dx. So again, taking the derivative of both sides with respect to x. Okay, so the left side will be fine because the left side just ends up being 2x. But on the right side, it is tricky because you're finding the derivative and there's x's and y's mixed together. And then also you have the quotient. You have a quotient. And so you must use the quotient rule. And this one is going to be kind of hard. So bear with me. So to do the quotient rule, we just do the derivative of the numerator, which will be 1 because the derivative of x with respect to x is 1. And then the derivative of y with respect to x is 1 times y prime. And then I just do it times the original denominator, and I don't change anything because I didn't take any derivatives. And then I do minus original numerator, x minus y, and then the derivative of the denominator, which would be the derivative of x with respect to x is 1, and then the derivative of y with respect to x is 1 times y prime, because the derivative of y would be 1, but then you have to multiply it by y prime every time. You do that because you're taking the derivative of x with respect to y. And then the denominator just stays the same. So that's first step. Let's just like make this look slightly neater. I don't know if I'll have space for this later, but that's okay. So instead of making it like, I'm just going to clean up this part. I'm just actually going to do 1 times y prime and then this part. So it might feel unnecessary to you, but I'm going to do that. Okay, so our goal now is to get these two y primes together. And then also I have a fraction, and so I like to get rid of my fractions when I solve. So my first thing that I am going to do actually is to get rid of the fraction on both sides, even before I try to get the y primes together, because having a fraction just makes everything complicated. So to get rid of a fraction, you just need to multiply by the denominator on both sides. So I'm going to do that first. And then, so my denominator is gone, and over here I'll have 1 minus y prime times x plus y minus x minus y times 1 plus y prime. So I got to get those y primes together, and the reason why this one is really a doozy is because I'm going to actually have to distribute if I want to get those two together, because they're both in parentheses and they're both in multiplication. So I need to undo the multiplication to be able to get those. So nothing on the left side is going to change right now. It's very unproblematic. But I'm going to come over here and I'm going to distribute these so that I can get the y primes out of the multiplication sign. So I'm going to do 1 times x, which is x. Then I'll do 1 times y, which is y. Then I'll do negative y prime times x, which will be negative x y prime. And then negative y prime times y, which will be negative y times y prime. So that's that part. Now the next part. And I'm, anything I get, because this is a minus sign, anything I get, I'm just going to flip the operation sign. So x times 1 is x, so I'm going to write minus x. X times y prime is xy prime, but because of this minus sign, it's going to be a minus xy prime. Negative y times 1 is negative y, because of that, plus y. And then finally, negative y times y prime is going to be negative y prime, but this makes it positive. And that's good because a couple of these things are going to cancel out, if you notice, because these are opposite, so these x's are gone. These are opposite, so these are gone. And then I think we just have a couple things left now. So I'm going to go back up to the top to my simplification because I need some more space. So I'll have 2x, x plus y squared. And then I'll have y minus xy prime minus xy prime plus y left. I can combine some like terms, and I'll get 2y minus 2xy prime. So I just combined these two y's, and then I combined these two because they're like terms. Now I can do some more work. So now I'm going to subtract 2y on both sides. And I'll get 2x times x plus y squared all over, or minus 2y, equaling minus 2xy prime. So if you forgot our goal here, because of all this algebra, the goal is to get y prime by itself. So that's why I moved 2y over. Now I'm going to divide both sides by negative 2x, and then I have my answer. 2x times x plus y squared minus 2y over negative 2x. You should show all your friends that you did this problem because it is so algebraically tricky and there are no room for errors. But this is your answer because you have y prime by itself. So you found the derivative of x squared equals x minus y divided by x plus y. And that is the answer, and it is so painful, but you should be proud of yourself. So let's skip the next problem unless you really want to do it. And we're going to do one more kind of problem, maybe two more kinds of problems. But I'm assuming that we have been watching this video for a very long time. So this one says find the derivative y with respect to x and find the slope of the curve at the indicated point. So x squared plus y squared equals 9 at 0, 3. So first we're finding the derivative. And then we're going to find the slope of the curve at that point. And so we'll get to that idea later. But I guess let me just show you. If you guys didn't know what that equation was, x squared plus y squared equals 9 represents a circle. And basically this, the square root of 9, the square root of whatever that like c value is the radius of the circle. So the radius of our circle is going to be 3. And then it's just a circle. So this is a circle. And then because the radius is 3, this is the point 0, 3. So it basically just wants to find the slope of the curve of this point. So the slope of the curve is essentially what is the tangent line at this point. What's the slope of that tangent line? You guys might already know what that is. It is 0. The slope out there is 0. So our answer to this question should come out to be 0. But let's just do it for fun. So we've done problems like this one. This one is so much easier than the last one we did. So I'm going to find the derivative on both sides with respect to x. That will give me 2x times nothing. 2x times, that's fine. Okay. And then the derivative of y squared with respect to x is 2y. Let's go back to dy dx notation. And then on the right side, that's 0. And then we just got to get dy dx by itself. We did a lot of problems that looked a lot like this. So this will give me negative 2x. Divide both sides by 2y. And I'll get dy dx equals negative x over y because these cancel out. And then I specifically want to find the slope of the curve at 0, 3. So 0 is an x value, 3 is a y value. And I'm going to plug in 0 for x, and then 3 for y, and then 0 divided by 3 is 0. And so that is the slope of the curve at the indicated point. And so just like all of our other derivatives are slopes of tangents, these are just slope of the curve is the same as asking for the slope of the tangent. So those are the same things. But these problems that you get just happen to be more slopey, more curvy, like they happen to be like more like circles. So this next one also is a circle. It just has a little translation in it. And so I'll get back to that part later. Let's just do the problem. So this one says find the slope of the curve at the indicated point. So I'm going to start by finding the derivative of both sides with respect to x. This is the last one we're doing, and then you're free. And none will be as hard as that really hard one that we did. Okay, so let's start by finding the derivative. So I have to use the chain rule here because there's an inside-outside function, outside function. So the derivative of this is 2 times x plus 2 to the 1 power, and then the derivative of the inside is 1. So yes, you have to use the chain rule, but like really it doesn't do anything because the derivative of the inside is 1. This next one, you would do the chain rule too. So this would be 2 times y plus 3. This goes to the 2 power, and then the derivative of y plus 3 is going to be dy dx because the derivative of y is 1, but then you always have to multiply by dy dx because you know the stuff, hopefully. Okay, the derivative of 25 with respect to x is 0. So now I'm just solving for dy dx. That's my goal once I take the derivative, and so I'm going to go ahead and move this term over here to the other side because I don't need it on that side anymore. And I'll have 2 times y plus 3 times dy dx equaling negative 2x plus 2. And then I will divide both sides by this. So I got dy dx equals negative 2x plus 2 all over 2y plus 3. And then I can simplify that down, but the goal for this problem isn't... Actually, let's just do it. That was so easy. I simplified. Okay. So this is what I get. And then because I want to find the slope of the curve at these points, I'll just go ahead and plug those in. So x is 1, so I'll do 1 plus 2. And then y is 7, so I'll do negative 7 plus 3. And I'll get negative 3 over negative 4. And so that answer is 3/4. And then that is the answer. So that's the slope of the curve. But say you had graphed this. This is roughly what that graph looks like. It's a circle again with a radius of 5. And then 1/7 is like 1 negative 7 would be like right here. And so the slope of this right here is 3/4. But that's what we did. We did implicit differentiation. If you really are just bored and you want to do more problems, feel free to do this one. And I'll tell you what the answer is later. But you can stop there. Good job for your hard work today.